Hello everyone, my name is Hui Chen from King Abdullah University of Science and Technology. Today I will present our work, Phase Difference-Based 3D Source Localization using a compact receiver configuration. The structure of this presentation is following: introduction, the proposed algorithm, error model and tracking strategy, simulation and experiments, and finally, the conclusion. Those are the 5 sections of the paper. Location information is important for many applications, such as object tracking, robot navigation, wireless sensor network, and gesture recognition. Sensor network-based localization is one of the important methods to obtain the location of a target. The system estimates the location information of the target using received signal strength, time of arrival, time difference of arrival, or direction of arrival. Then, a triangulation or transliteration algorithm is implemented to obtain the target position. Although the deployment of the sensor networks provides sufficient localization accuracy, the number of the base stations required in those methods increases the complexity and the cost of the system. We propose a compact receiver configuration to solve the mentioned issues. The compact here has 2 meanings: minimum hardware resources and the minimum efforts for deployment. The single base station solution provides small system calibration errors and small array size, which is suitable for the mobile devices. The localization model is shown on the left figure. A transmitter periodically sends signal blocks, which are received by a planar receiver array on a base station. Each block consists of sinusoidal pulses with frequencies of f1, f2 to fn, where capital N is the number of frequency components. The pulses have the same duration Tp and are transmitted sequentially inside each block. The receiver array contains a 2D circular DOA subarray centered at the origin of the coordinate system for DOA estimation, and one ranging receiver located at V with the relatively large distance from O. Alpha, beta are the angles between the target direction vector and xy axis, respectively. With known DOA estimated by the circular array, the localization problem is simplified as getting the range R by looking at the plane W, which is formed by points O, V, and T. We have the path difference model, as shown on the left figure. For a target T at range R, the distance between the target location T and anchor U and V can be expressed as RU and RV in equation 4 and 5. The relationship between the path difference P and unwrapped phase difference phi can be expressed in equation 6. The derivative of P with respect to R can be expressed in equation 7. We can prove if R is greater than V, greater than U, greater than 0, the inequality 8 holds, which means 7 is positive. This indicates that for a fixed alpha, if the value of the estimated unwrapped phase difference is known, there exists only one value R corresponding to the path difference P. Then we can estimate range using Nye. Now we will explain the localization algorithm. The first step is phase difference estimation. In practice, the path difference, which is the unwrapped phase difference, cannot be obtained because of phase ambiguity. The observed phase difference vector from the 2 anchors is wrapped into minus pi and pi. One example is shown on the left figure where the unwrapped phase is rounded into several segments. However, we can use multiple frequencies to solve this issue. For an observed phase difference vector, we search the range in a candidate set R1, R2 to Rm along the DOA of alpha and find the range that matches the observations best. In this way, the estimation in 3D space is simplified into a 1D problem, which reduces the algorithm complexity. This candidate set can be chosen, for example, with an increment of 1 cm from 0.3 meter to 4 meters, depending on the requirement of detecting range and computational resources. Then, for a hypothesized range Rm, the corresponding observed phase difference vector can be calculated as equation 11. The estimated range can be obtained by finding the candidate that maximize the cost function in 12. The range estimation by solving equation 12 will not always work. We can, however, derive a sufficient condition, which is the equation 16 are not satisfied. Then the localization algorithm can be performed in 5 steps. First, obtain direction vector t using DOA algorithm. Second, calculate the wrapped phase difference vector using 10. Third, define range candidates set and calculate the corresponding observed phase difference of all the candidates using 11. Fourth, calculate the estimated range using 12. And finally, obtain the 3D location of the target using 3. We will use an ultrasonic signal to verify this algorithm. The parameters of an ultrasonic system are chosen as alpha equals to 90, u equals to 0.9 cm, v is 14 cm, f is chosen as 18 and 21 kHz. The detection range is from 0.2 meter to 3 meters when the searching resolution of 1 cm. Now we will visualize the phase difference vectors in equation 12 for the case of n equals 2 frequency components. Figure A shows the phase difference vector with the mentioned parameters. In noise-free case, if the phase difference is inside the red area, the estimation range will have the error smaller than 1 cm. As the points are getting closer when R increases, performance deteriorates because the red area is smaller, indicating a lower probability to have a small error. This is also easy to understand intuitively because the setup tends to be a far-field model when R is large. In figure B, a large V will sparse the candidates. It indicates a better result based on our previous conclusion. In figure C, if we change alpha to 91 degree, the locations are shifted compared with figure A, and hence error occurs. In figure D, if we choose f as 18 and 23 kHz, a large distance capital L between two lines is shown a better performance. We define the error level with wavelength and the derivative of P. This indicates the range estimation error caused by the unit wavelength error in phase difference estimation at R. From the figure, it's reasonable to perform a tracking after synchronization strategy, using the first several measurements as initial range estimation and using the relative movements obtained by cross-correlation to get the rest of the range estimation as 18. In simulation, we compare the proposed 4-anchor setup with 2 other setups. The parameters are shown on the left. In simulation, the parameters are not changing a lot. In experiment, the sampling frequency is chosen as 96 kHz. Tp is 2 milliseconds, N is 3. The RMSE for different methods and frequencies are shown on the left. The performance is satisfactory with 4 sensors. When increased to 6 sensors, the results are better than the method in 9. The experimental tests have 2 parts, fixed DOA test and fixed range test. Performance drops fast with R and alpha. However, the accuracy can be improved with more sensors, frequencies, a larger V or averaging multiple estimations. In this paper, a 3D positioning system is proposed by utilizing a compact receiver setup. A localization algorithm for this specific setup is proposed. Several factors affecting the system performance are discussed. Those are all the references of this paper. And thanks for your time.